Okay, now the important part is now efficiency, to calculate efficiency. So efficiency of an power amplifier is the ratio of AC output power to the DC input power. Okay, so this is basically the ratio of the AC. This one is AC output power, this one, okay, and the DC input power. So efficiency is the ratio of two powers, but we over here we just check another parameter and we say how actually remember that in amplifier, in whenever we talk about amplifier, we have what we have the biasing network. Okay, the biasing network, okay, R1 and R2, which is connected to VCC, okay, VCC, and then we have what we have the input signal as well, okay, which is V in a sinusoidal signal, right? Okay, this is the sinusoidal signal. I can make it ground over here. Okay, again this is ground, and I can say this is rather if I go, oh, sorry, okay, I can make a load resistor over here. I can see I can ground it over here. This is your RL. Okay, so the P out is somewhere over here. This is your AC. So what is P out? Okay, but not from P out is, which is a function of P in. Remember, P out can be a function of, we can call it PDC. Okay, we can say that is your DC power, but over here this is P out. P out means AC power. Over here we mean AC power. So because of V in, how much power appears at the output of the power amplifier, remember. And PDC is actually what is the input power, DC input power, because of this VCC DC supply voltage over here, remember. So basically again I repeat it, that this P out is we call this, we consider this as P out, the AC P out, and PDC is the DC power because of the VCC, right? So basically we are mixing things. Remember, this efficiency gives us that, okay, if you have the input signal, sinusoidal signal, and the biasing applied at the input of the amplifier, so how much efficient this amplifier is. So it would be the ratio of P out to PDC, right? Okay, now I can I prove this thing, that the maximum efficiency of class A amplifier is 25% when operated at Q point. Can I prove this one? So I can, okay, how can I prove? Over here I can go into this equation. What is P out? P out would be VC, okay, times IC, right? Okay, and then divided by PDC would be remember it was ICEQ. Okay, PDC is the quiescent point, okay, and VCEQ, okay. But remember, we said that we put this VCEQ at the quiescent point. Okay, it is 2 times, okay, 2 times of the VCC. So it's basically, I can say this is 2 VCQ. Okay, because we are dealing with operated at the Q point. So when Q point is operated at the midpoint, okay, for class amplifier, VC basically is equal to 2 times VCQ, right? Okay, and I can say now this is AC, this is also AC current, this is AC voltage. So I can further write this as equal to VC. I can write this, I can convert this into RMS, so I can put it 0.707 times VC. Okay, this would be RMS into, okay, again 0.707 point, so I can write this is 0.707. Okay, and the current value I can put is IC, okay, IC, and I can have this as equal to 2 VC, okay, VCQ, okay, and this is ICQ. Okay, I can also write this is VCQ for the quiescent point I'm interested at the quiescent. So I can write a subscript VCQ in ICQ. So it means that this ICVCQ cancel with this one. Okay, this times this 0.7, it will be 0.5. So I can write this as equal to 0.5 divided by 2. So it means this is equal to 25%. 25% over here, which is actually what it is. Actually, you can write this as 0.25. The 0.25, right? Okay, so 0.25 in percentage means 25%. So it means that the quiescent point, okay, the maximum efficiency you get for class amplifier is 25%. The rest of 75% it is dissipated as heat. So it means that is not a very good power amplifier, class amplifier, because we are losing 75% of the power which is dissipated at heat. Okay, so now next slide please. You can go there, I can see over here, right? Okay, over here now it says they determine, this is example 7.2, determine the efficiency of the DC power amplifier, okay, in figure 7.5. So this is the same figure, same circuit. This is the common, this is the main driving amplifier from here to here, okay, and then this is your Darlington pair, okay, this one is your Darlington pair, and this is the load. Okay, so we can see this is three basically multi-stage amplifier, right? Okay, the same thing. Now it says they determine the efficiency. So straight away efficiency by definition is P out, okay, and divided by PDC. Okay, now I can go in to calculate P out. I can say P out is VC into IC, and I can put the value. But since I know from the previous part that AP, the power gain, okay, is from the last part, let's suppose it has some value, let's suppose 10,000 or 1,000, okay, or maybe any value, let's suppose it was calculated as 1,000, okay, P in, okay, so I can, using this relation, I can also use the point I'm making, that I can use VC and IC, take the product, convert this into RMS 0.707 VC, 0.707 IC. But since this is one thing, but since AP is given, so straight away I can use the relation that AP, okay, power gain is equal to, okay, P out divided by P in, P out divided by P in. Okay, so I need to find P out because I'm interested in this value. So that's why I can put the value P. I find this is known from the previous part. P in I need to find. So by definition, P in is V square divided by R. I put the subscript in and in to denote P in. So V in square over here 35.4 milliwatts. Okay, now this is peak to peak, remember, so 50 times, okay, milliwatts into 0.707, right? So you'll get this value 35.4. You square it, right? Okay, divide by R in, okay, the input resistance you calculated from the previous part, it comes out to be 8.4. So P in comes out to be 149 nanowatts. Okay, if all the value to be concerned. Okay, now so I can put the value, this one over here, okay, and the gain was I calculated, no need to calculate again it, okay, and then this comes out to be P out as this value. Okay,